All right, in this video, we are going to learn the basics of trig. So right there's a little blurb that I encourage you to read for yourself. Basically talks about where the word trigonometry comes from. It just means the measurement of triangles and their angles and their sides. Since about the 1700s, when calculus and physics were developed, people started studying trig relationships like SOHCAHTOA, and it allowed us as humans to discover things about sound waves, planetary orbits, music, like the way strings vibrate, and just kind of led to a boom in mathematics. If you want to learn higher maths like calculus, it's really important to have a strong trig background. And it's very interconnected, so if you like math, you're going to really like trigonometry. All right, so the first term that you're probably familiar with are degrees, degree measures, how you measure an angle. Now, it's not the only way to measure an angle, all right? If the idea of degrees stems from a full circle being 360 degrees, all right? So that's like one revolution. So like if you started here and walked or turned around like a full revolution, then that's equal to 360 degrees. So we use the fraction of that to help us find different angles. So like half of 360 would be 180, or a quarter of 360 would be 90. And it's actually kind of interesting if you were to, it's kind of arbitrary that there's 360 degrees in a circle. The reason why that was picked is because we used to have a base 60 number system. And also there's just divisible by a lot of numbers. 360 goes divisible by 2, 3, 4, 5, 6, 8, so on and so forth. But it's interesting if you think like, you know, if a circle was 100 degrees, it could have been, there could be an alien life form that has 100 degrees as a full circle, then now 90, or what we know as 90 degrees would be like a 25-degree angle. So there are other ways to measure angles, and we will learn about them. But for now, we're going to use degrees. And again, it's kind of just an arbitrary thing if there's 360 degrees in a circle, and everything else sort of stems from that. Okay. Now what I'd like you to do is to write down the definitions of these words. So if you pause the video, either write down what you know, and if you don't know, like look it up. And then once you hit unpause, once you play the video, you'll be able to see what the answers are. All right, I'm trying new things here. I thought I'd be able to write it all out, but I can't. So let's just start. So acute angle is an angle that's less than 90 degrees. So less than 90. So think of like something acute, something small, something that's less than 90, and I use the wrong symbol there, that's my bad. So if X is the angle, X is going to be less than 90. And then an obtuse angle is more than 90. So any angle that's bigger than 90 is obtuse. A right angle is an angle that's bigger than 90. So, sorry, I'm losing my mind. It's equal to 90 degrees. So a right angle is exactly 90 degrees. A straight angle would be 180 degrees. Complementary angles are angles that add to 90, all right? Angles that add to 90. And there's a way to remember that, but I guess we'll learn about supplementary angles first because they're kind of related. Supplementary angles are two angles that add to 180. So the way I remember that is I think of the C in complementary and the S in supplementary. And if you look at the C in complementary and you add a line right here, okay, it looks like a 9 for 90 degrees. So complementary angles add up to 90. And the S in supplementary, if you put a line right there, looks like an 8. So that's like a 180, 8 for 180 supplementary. All right, so those are some important vocab terms that we're going to need going forward. All right, now let's talk about the Pythagorean Theorem. So in a right triangle, the sum of the legs of squared is equal to the hypotenuse squared. In other words, a squared plus b squared equals c squared. A and b are the lengths of the legs in a right triangle, and c is the length of the hypotenuse. All right, so we use this to find the missing length of a right triangle. So first, I'd like you to try this proof of a Pythagorean theorem. there's like thousands of different proofs of the Pythagorean theorem. Of different presidents have their own proofs. It's Pythagorean theorem has been around for thousands and thousands of years. The ancient Egyptians, we have evidence that they used it. The ancient Chinese used it. The Mayans. Something that was discovered independently a long time ago, and it's great for finding distances, among other things. So I would say pause the video and try this proof on your own. So use the square to try to prove that a squared plus b squared equals c squared. Now, if you look, a and b are the legs of the triangle, and c is the hypotenuse. So when you write a, b, and c, that's what they refer to. And the hint I give you is to write the area of the square two different ways. All right, so right now would be a good time to pause the video, and I'll show you how to do it. All right, so the first way we're going to do it is to write the area of the square by using just the side lengths of that big square. So if one side is a plus b, and since that's a square, the area is going to be a plus b squared. All right. Now, if we simplify that, or not simplify it, but multiply it out, it becomes a squared plus 2ab plus b squared. Okay. Now, another way that we could relate or express the area of this square is to write the area of these four triangles and then add the square in the middle. So there's four triangles where the base is a and the height is b. So 4 times ab, and then divide by 2, because base times height divided by 2 is the area of a triangle formula. All right, then add this middle area here, which is a square, so plus c squared. All right, so that's going to simplify to 2ab plus c squared. Now, we set them equal to each other because they both represent the same area. They're both squares. All right, so that equals that. All right, now if you look, there's a 2ab on both sides, so we can subtract it, and we get a squared plus b squared is equal to c squared. All right, so there's a fun little proof of the Pythagorean theorem. So now let's use it to find this missing length here. Whoops. So find the length of x. So we have an isosceles triangle. All right, I know it's isosceles because the two side lengths are both x. Okay, now when you have an isosceles triangle, when you draw the height, it's also going to bisect this side on the bottom here, making that 8 and 8. Now the reason why has to do with congruent triangle stuff. All right, we know that these two sides are equal because they're both length x. Okay, we know that that's a shared segment, and we know that both these angles are right angles because that's a height. So by hypotenuse leg, the two triangles are congruent. So by CPCTC, these two sides have to equal each other, which is why they both have to be 8. Okay, so now we could do the Pythagorean theorem by labeling this side A, that side B, and that side C. I could have switched A and B, it wouldn't have mattered, but C had to be the side length x because it's the hypotenuse. So then we get 8 squared plus 15 squared is equal to c squared. All right, 64 plus 225 is equal to 289 is equal to c squared. Take the square root, and you get that c is equal to 17. So that's the length of x. All right, moving right along here to special right triangles. So at this point, you might want to pause the video and watch or try that investigation. I'll share these notes with you. Unless I didn't, then don't worry about it. But if you need a review on special right triangles, there's a good investigation right here. And I also made a video on special right triangles. If that doesn't make sense, or if you want more review, it's right there. So I would pause the video right now and do some special right triangles review, because that's also important to trig basics. All right. Now, so I'm not going to say much about that because it's all there. I don't want to bore you guys. All right. Now let's look at different trig functions. So in a right triangle, theta is one of the acute angles. So theta is something we're going to talk about a lot. It's just a Greek letter. Okay, it looks like a circle with a belt on it. Okay, and it's used to represent angles that we don't know. So when you're using these definitions, theta has to be one of the acute angles. So it could be this angle or it could be that angle, okay? Now, the hypotenuse is the longest side of a right triangle. It's across from the right angle. The opposite leg is across from theta. So if theta was here, that's the opposite leg, okay? If theta was here, then that's the opposite leg. So that's why it's important to establish what angle we're going to work with first, okay? Then if we're using the orange theta, that's the adjacent leg because that's the leg next to theta. That's not the hypotenuse, right? The hypotenuse is right here, okay? And if purple theta is the angle we're looking at, then this side right here is the adjacent leg. So these are the trig definitions. So katoa is a way to remember it. So meaning sine is equal to opposite over hypotenuse. Ka meaning like cosine is equal to adjacent divided by hypotenuse. And tangent is equal to opposite over adjacent. All right, so sine, cosine, and tangent are just the ratio of two sides of a right triangle. Now, this stuff down here, we'll study more later on. Don't worry about it yet. But they're just the reciprocal functions. So, like the reciprocal of sine is hypotenuse over opposite. You just flip that. Secant is the reciprocal of cosine, so it's just adjacent over hypotenuse flipped, which would be hypotenuse over adjacent. Tangent is O over A, opposite over adjacent. So cotangent is the reciprocal of that, adjacent over opposite. Okay, so let's apply some of these with the problem down here. So given that the tangent of theta is equal to 4/3, find the value of the other 6 trig functions. So helps to draw a picture, okay? So if I make theta that angle right there, the opposite leg is going to be 4 and the adjacent leg is going to be 4. Now that doesn't have to be the ratio. I mean, that doesn't have to be the side lengths per se, but it will have to be the ratio of the sides. So like theoretically, like this side could be 8 and that side could be 6, or this side could be 40 and that side could be 30. All right, but since all triangles with the same ratio of 2 legs and the angle in between are congruent or similar, we could just use 4 and 3. So we could use the Pythagorean theorem and figure that this side right here is 5. Now we're going to use theta to identify these legs as opposite, adjacent, and hypotenuse. All right, so then the sine of theta is going to be opposite over hypotenuse, 4/5. The cosine of theta is going to be adjacent over hypotenuse, right? That's going to be 3/5. Tangent we know is 4/3, all right? And then it said all 6, so cosecant of theta is just the reciprocal of sine. So if sine was 4/5, this is going to be 5/4. Secant is the reciprocal of cosine, so that would be 5/3. All right, and then cotangent is the reciprocal of tangent. That's going to be 4/3 flipped. All right, so 3/4. All right, so that's a little introduction to the different trig, just trig definitions. All right, so now this activity here, I encourage you to pause and try this on your own. So you have a right triangle. Well, you really have a 28-degree angle here. So if you look at angle like DAG, it's 28 degrees. Okay, let me highlight that for you. This angle is right here. It's 28 degrees. Sorry, having some technical difficulties. This angle right here is 28 degrees. So every time you draw a perpendicular line here, you create a triangle that's similar to the other triangle because they all have the same angles, all right? So what I want you to do in this activity is first, like look at the red triangle and find the tangent of 28 degrees. And then look at the orange triangle and find the tangent of 28 degrees. All right, then look at the yellow triangle and find the tangent of 28 degrees. All right, so if you want to pause the video and try that, and then we'll summarize it together, that would be a good time to do that. All right, so first tangent of 28 that I got would be 2.07 over 3.88. Okay, that'd be the tangent of 28 degrees. Then if you use the bigger triangle, like this one right here, all right, the tangent of 28 would be 3.13 divided by 5.88. All right, I got 5.88 by adding these two together. Okay, then if you look at the bigger triangle, okay, the tangent of 28 is going to be 4.24 divided by the sum of all these three sides. So that would be 5.88 plus 2.09, which is 7.97. Now, if you were to divide all these fractions and get a decimal, you would see that they all come out to be about 0.53. All right, so in other words, this, all equal about 0.53. Now, if we look at our calculator, so I have that up already, so I'm going to pull up my calculator. And I type in the tangent of 28. Do Control Enter to get it as a decimal. All right, you see it's about 0.53. All right, now there's a reason for that. And let's look at one other thing. There's these things called the Trig Table. If we look at this Trig Table, notice how the third column here is tangent. And we go down to 28, we see it's the same number, 0.5317. Okay, now trig tables are just stored in your calculator. So that's how the calculator knew the answer. But where did trig tables come from? Well, you can read about them down here, but I'll describe them for you right now. So a mathematician a long time ago, a couple hundred years ago, did this experiment that we just did with 28 degrees. He or she, the mathematician that did it, understood that all triangles with the same angle measures are similar. In other words, this triangle is similar to that triangle, similar to that triangle. So the ratio of their sides are all going to be equal. So if you know that the ratio of the opposite leg to the adjacent leg in a 28 degree, this angle would be 62 degree, 90 degree triangle, if you always knew it's about 0.53, then if you knew the opposite leg, you can use that ratio to find the adjacent leg. Or maybe you know the opposite leg and the adjacent leg, and you know the ratio is 0.53, and that'll help you figure out that this angle here is 28 degrees. So just like you use special ratios to solve special right triangles, all right, this is the same idea, except you don't have to memorize those ratios. They're stored on your calculator or stored on a trig table. Okay, so that's pretty much where these numbers come from. They're not random. So if you read more here, like someone did this experiment with a 1 degree angle and then a 2 degree angle and a 3 degree angle, and then used a protractor and ruler and measured all the sides, divided those numbers, and then made this table right here. All right. And if you look at this table, it makes a lot of sense, right? The sine of 1 degree is very small. That's because in a 1 degree angle, okay, if I were to draw that, this angle is 1. It has to be a right triangle, so this angle is 89. Obviously, if this side is x, this side here is going to be like 0.0175, the length of x, meaning it's going to be about 1 to 2% the length of this entire side, which makes sense because this angle is so small, which will make that side small, and this angle is big, which will make x a lot bigger than that. All right, so what do you think? Think about this. What do you think the tangent of 45 is? All right, pause the video and think about it. What do you think the tangent of 45 would be? Well, if we scroll down here, down this trig table, we see that it's 1, right? And it should make sense because if we had a 45 degree angle and a 90 degree triangle, or a right triangle, right, that angle also has to be 45 degrees. So like no matter what side this is, this side also has to be 5. So if you do the tangent of 45, 5 over 5 is 1, a 1-to-1 ratio, which that's why 45, 45, 90 triangles have equal legs, all right? If you look at 30 over here, it's 0.5. That's because in a 30, 60, 90 triangle, the opposite leg is going to be half the hypotenuse, no matter what, whether that's 10 and 20 or 1 and 2, that relationship is always going to be true, all right? So again, this trig table is just like special right triangles. You treat them the same way, except you don't have to memorize the ratios. They're all here for you. And you don't even need a trig table. It's all stored on your calculator. Right? And then inverse trig is just when you're looking for the angle and you're given the ratio. So if I wanted to know, if we look at this right here, if I wanted to know what the sine of 30 was, I would plug in 30 into sine and I would get 1/2. in math, inverse means to switch the domain and range. So if I wanted to know what angle I was taking the sine of to get 1/2, I would flip my input and my output, but I would use an inverse function instead. So I would use sine inverse. And then it would tell me that the sine inverse of the sine inverse of 1/2 is 30. So if you don't know what the input is, you can use the inverse to flip the input and the output, right? And I'll show you what I mean by that, but pretty much you're going to use inverse when you're looking for an angle and just use sine, cosine, tangent when you're looking for the ratio. All right, so now let's apply all that to this problem right here, and that'll be the end of this video. All right, so first we have to solve for all these missing sides and angles. All right, and actually, I'm going to make this picture a little bigger so I have room to work here. Okay, so this side right here, we'll call it X. Okay, since it's opposite of 41 and I'm given the adjacent leg, I'm going to use tangent because it's opposite and adjacent. All right, so that's, we look at SOHCAHTOA. When we're using opposite and adjacent legs, we're going to use tangent. If it was opposite and hypotenuse, you're going to use sine. Adjacent, hypotenuse, cosine. All right, so the tangent of 41 is equal to x over 9. All right, now I'm going to take my calculator and type in the tangent of 41. All right, if you're not sure where to find that on your calculator, I will show you right at the end, but if I forget, just ask. All right, so the tangent of 41 is 0.869 is equal to x over 9. Now we're going to cross multiply, and you get that x is equal to 7.82. All right, so now we know this side right here is 7.82. Okay, this angle here, all right, the angle that I highlighted in orange is going to be 49 degrees. All right, that's because the three angles of a triangle have to add up to 180. All right, now this angle here, or sorry, this side here, all right, we'll call it y. All right, we don't need to do SOHCAHTOA here. You could do the Pythagorean Theorem. So like one way to find y would be 9 squared plus x squared, which we know is 7.82 squared is equal to y squared. All right, that would work. Another way we could do it, all right, so this is a separate way of doing it, would be using sine. Since sine is opposite over hypotenuse, you could do x, which you know is 7.82 over y, right? Or you could also do cosine of 41 is equal to 9 over y, right? Either of these methods will work. 1, 2, or 3 are all different ways of doing it, all right? I'm going to do the last way just to give us a practice with cosine. All right, so now I'm going to cross multiply. So when I cross multiply, I'm going to put cosine of 41 over 1, and I get the cosine of 41 times y is equal to 9. Then I could divide both sides by the cosine of 41, and I get y is equal to 9 over the cosine of 41. All right, I could type that in my calculator because remember the cosine of 41 is just a number, and when I do that, I get 11.9. So y is equal to 11.9. All right, so now that's that side right there. Okay, so now to find, all right, let's find an angle now. So let's look for this angle here. We'll call it, we'll just be angle L. All right, so angle L, we know the opposite leg and we know the hypotenuse. So opposite and hypotenuse is sine. So that means the sine of angle L is equal to x, which is 7.82 over 21. Now, that means, as a decimal, that the sine of L is equal to 7.82 over 21, which is 0.372, okay? Now, if we had a trig table, all right, we could pull it up and see, all right, what angle would I take the sine of to get 0.372 or something close to that? Right? But you're often not going to have a trig table handy, but you will have a calculator. So when you're looking for the angle, that's when you use sine inverse to switch the input and the output. And now this on the calculator will tell me what what this angle L is. And I get, when I type that in the calculator, L is about 21.8 degrees, okay? So if angle L is 21.8 degrees, then we could use that to figure out angle MKL. So the measure of angle MKL is going to equal 180 minus 90 minus 21, which would be 69 degrees, right? 21 plus 69 is 90, so good, okay? And then last but not least, all right, you could find this side right here by doing the Pythagorean Theorem. All right, so if you did x squared is 7.82 squared plus, yeah, it kind of looks bad. So 7.8 squared will round plus x squared, or we'll call it ml squared, all right, equals 21 squared. Now, what you have to do is subtract 7.8 squared from 21 squared, and you get 380, which is equal to ml squared. Take the square root, and you get 19.5 roughly, right? So this side right here would be about 19.5. All right, so that's your crash course in trig, the basics of trig. Hope you find it helpful, and thanks for watching.